Hello and welcome to this lecture series on chemical process modeling and simulation. We are into a set of lectures now on modeling energy of systems, and we've been discussing the fundamentals of thermodynamics. And we started with an introduction to the basic concepts, and then we derived the criteria for thermodynamic equilibrium, and then we try to understand what entropy means in one lecture. So after those three lectures, the fourth lecture in this series is on it's of three parts. Each part is going to present to you an understanding of different intensive properties. This part, the first part of this lecture, this is on temperature, and then there will be one on pressure, and there will be one on chemical potential. So this lecture series is going to be three-part mini series on temperature, pressure, and chemical potential. So what is temperature? So I state here that temperature is the driving force for energy exchange between system and its surroundings, or two subsystems within the system, so as to maximize entropy. So we start this with the entropy formulation, which we discussed in the last lecture, right? So what does the entropy formulation state? It states that the macroscopic state of a thermodynamic system can be defined by its entropy. Similar to the internal energy formulation, we saw that both these formulations are interconvertible and invertible. The internal energy formulation states that the macroscopic state of a thermodynamic system is defined by its internal energy, and there you consider various independent variables to describe the state of the system, and therefore internal energy is a function of a set of variables. Whereas the entropy formulation hypothesizes that the macroscopic state of a thermodynamic system is defined by its entropy, and therefore entropy is a function of many independent variables. And how many variables? For the systems that we are considering in this course, we are looking at three independent variables as per the state postulate. One for the heat interactions, the plus one, and then we are looking at two work modes. One is the work mode related to expansion of the boundaries of a system, resulting in moving boundaries being, causing expansion or contraction, and that is driven by the difference in the internal pressure of the system versus the pressure exerted from outside, right? And then here, this one is the third one, is the work mode available due to the permeability of the boundary, which basically can allow species to diffuse through the boundary to the surroundings or into the system. Again, we are looking at characterizing the independent the work mode by way of how many moles of species is present. Either it is, you can measure it as number of moles, or any other unit, that is any other variable that you could use to measure the amount of substance that is present, right? So these are the three variables that we are considering for defining the macroscopic state of a system. And since that state is defined by the entropy of the system, entropy is a function of these three variables. Now therefore, if there were any differential change in entropy, and that change in entropy could arise due to a differential change in internal energy, or a differential change in volume, or a differential change in number, and the corresponding slopes for each of these is given by dou s dou u at constant Vn, dou s dou v at constant Un, dou s dou n at constant uv. These are the three partial derivatives. This is how partial derivatives are defined. Now we further assign 1 over T to be inverse of temperature to be dou S dou U at Vn, which means temperature would be dou U dou S at constant Vn. And we assign P by T, pressure over temperature, to be dou S dou V at constant Un, and we assign with a negative sign mu over T the chemical potential over temperature to be dou S dou N at constant UV. We just give these variables, and therefore using this we define the three intensive properties. Keep in mind that S is an intensive property, extensive property. U is also an extensive property, and therefore this partial derivative has to be an intensive property. So is the case here as well as here, right? So that's how we define the various intensive properties. So in this lecture we will be talking about what is temperature and what is the meaning of this intensive property. So thus we can, in this entropy formulation, we can simply write ds is equal to 1 over T du plus P over T dV minus mu over T dN, right? So we are going to spend the rest of this lecture on understanding temperature, thermodynamic temperature, and specifically understanding this partial derivative. So let's try and first give a physical interpretation for what temperature is. Let's start with these questions. Does heat flow in order to equalize energies? When I say heat flow, naturally there are two systems, or at least two subsystems within a larger system. So heat flows from one system to another system. As you recall, heat is energy in transit, and therefore you cannot assign it to a single system. You have to assign it to two systems, and you also have to assign a direction from which system to which system is heat flowing. So when it is asked, does heat flow, okay, between two systems so as to equalize energies? No, heat does not flow so as to equalize energies. If that were the case, I could take, for example, a simple glass of water, hot water. I've kept in a glass and I leave it on my table. It is exposed to the ambient conditions, all right, and so the hot glass of water is losing heat to the ambient conditions. If I were to look at the entire ambient of all the substances that are present in my room, for example, a table, my laptop, and a bunch of books, there is air, there are chairs, there are so many things that are present here. If you were to put all that energies of all of them together, that would probably far exceed the energy that is contained in that glass of hot water. So we are not trying to equalize energies here. Heat flows to equalize temperatures, and in doing so maximize entropy. This is the key idea in heat exchange, right? The mode of energy exchange as thermal energy. So temperature measures the driving force for energy exchange, and when I say energy exchange, it has to be specifically connected to heat. Okay, there are other modes of energy exchange which can be due to mechanical movement of boundary, which is the pressure based work, and actual exchange of species. So some material is added to the system or removed from the system, that has got to do with potential, and all of them are energy exchanges, and that is why you see in the intensive properties for the energy exchange due to moving boundaries or due to diffuse permeable boundaries, right? You see 1 over temperature also showing up in each of those cases, right? But if we are looking at temperature alone, it measures the driving force for energy exchange in the form of heat. That's why I started this whole physical interpretation with this specific leading question. So temperature measures the driving force for energy exchange between systems so as to maximize entropy. And this is basically coming from the hypothesis that we posited, that the rest state or the equilibrium state of a thermodynamic system is the one that corresponds to maximum entropy. And temperature measures the driving force that is available in the system in order to maximize entropy by exchanging energy as heat. So if we are to ask ourselves work, all of these are work modes with the exception of course, this one particular mode of energy exchange which we call as heat. Right? When we talk about work, what do we understand by work? Work is described as an energy in transit due to some force acting on a distance. And you say that whatever work is done on the system is stored as potential energy in the system. So you basically bring, for example, some charge from infinity to certain distance from a standard charge that is present at origin. Then you have done work in displacing that charge from infinity to that point, and that work done is stored as potential energy of interaction between these two charges, right? So this is how you describe work done. So for a conservative system where there are no dissipative losses of energy, right? So if there is no loss, then you can then simply write dW, which is basically a differential amount of work that is done by a force that is being exerted on the system, right? So that causes a certain displacement. So F dx is dW, and if these two are not in the same directions, you take the inner product or the dot product, and then you get the differential amount of work that is done. And so the total work that is done is simply integral f dx, and the force itself is simply the gradient of w with respect to x, the differential derivative of w with respect to x. So this is how you define basically work done. So larger the force that you apply, greater the amount of work that is done, isn't it? Viewed in a similar manner, if you were to look at this, ds is 1 by t du, entropy is now the potential, right, to displace energy, right? And 1 by t, inverse of temperature, is the driving force for it. Okay, so this is a sort of a simplistic picture, but you know, it sort of appeals to what we are trying to create as an understanding of what temperature is, right? So temperature is the driving force for the system to displace its energy, right? And entropy is the sort of change in entropy is the sort of work done or some sort of a change in the potential. So higher this temperature, higher the tendency, greater the tendency for the energy to be displaced from the system. This is something that we understand very well in practice. And therefore, the temperature is the driving force, and entropy measures the tendency of energy to escape from the system, right? Just as work measures the tendency of force to do a certain amount of work on the system. Now, entropy measures the tendency for this energy to be escaped due to the driving force called temperature. So this is one illustration of what temperature means. Now let us consider a simple analogy with money, with a financial transaction. Money represents capacity to produce things, just as energy represents capacity to do work, right? So money flows between people, just as energy flows between objects. When one person pays money to another, it is similar to two bodies that are exchanging energy. So one body is giving energy to another body. Conservation of energy is like conservation of money. In all financial transactions, the total amount of money is conserved, just like the total amount of energy is conserved in all interactions. This is captured by the first law of thermodynamics. But what is important to understand is that the exchange of energy between two systems is not driven by the tendency to equalize the distribution of energy. Just as when some person pays another person money, I mean, I'm just calling this person as rich person, the other person as poor person, just in quotations, just to sort of appeal to your sense of understanding of this. Okay, so when one person pays the other person, it is not to equalize their wealth, right? It is for something else entirely in a transaction. Let's look at an example. Suppose a person A has money, and that person wants a gadget. Could be a cell phone, mobile phone, or it could be a charger or anything. And suppose person B has gadgets to sell. So person A will benefit by paying money to receive the gadget. Person B will benefit by receiving money and thereby selling the gadget. This is what the financial transaction is all about, right? Just as we are now looking at exchange of energy, right? So what drives this transaction? The transaction is driven not to equalize the distribution of wealth. Money is exchanged because both parties gain some benefit. Economists call this business transaction, say money for gadget, as maximizing some sort of a utility function, this benefit. So maximizing the benefit, both parties' benefit has to get maximized in the business transaction. That is what is the ultimate goal. Money flows so as to increase the overall utility function for both parties. Similarly, energy flows when there is an increase in the overall entropy of the systems that exchange them. And this is, the increase is when there is an irreversible exchange of energy. When there is a reversible exchange of energy, then there is the overall entropy stays the same, it doesn't get decreased. ds is greater than or equal to 0. That is your third law of thermodynamics, right? So ds is equal to 0 for a reversible system, ds greater than a reversible process reaching an equilibrium. When you have an irreversible process, then ds is greater than 0. So the increase in the overall entropy happens when energy flows. This is captured by the second and third laws of thermodynamics. So what is temperature in all of this? Based on this definition, 1 by T being dou S dou U at constant N, the inverse of the temperature represents how much increase there is in entropy due to the exchange of energy. Because I increased the amount of energy, okay, how much did I increase the entropy? In other words, because this, money is exchanged just as energy is exchanged. So because there was an exchange of energy, how much benefit did I gain, did I accrue? So that is what is measured by the temperature. Once again, I repeat, because I exchanged money, I paid money to buy a gadget, or I sold the gadget for some money, whatever it is, either side of the financial transaction, how much benefit did I gain? And this is what is measured by the temperature, or inverse of the temperature. So this analogy is the increment in utility or benefit accrued by the business transaction, money for gadget. When these incremental benefits are equal, in other words, for the two parties involved in the business transaction, okay, the buyer has paid the correct amount of money to the seller, has received the gadget in the good working condition. Similarly, seller has received the correct amount of money for the gadget and sold the gadget in good working condition, right? So when this benefits for both parties are equal, there is no further net redistribution of money or gadgets, which is why we have a warranty system, right? So you have a warranty that this gadget will at least work for a certain period of time. If that is not, if that is the quality is not good enough and the gadget fails, to work for whatever reason, well, there is an imbalance. The money that has been already paid for the gadget is for the gadget to work at least for a certain period of time, and therefore now the gadget has to be either fixed or replaced, isn't it? So you go, this financial transaction continues until the incremental benefits for both parties are equal. Similarly, energy will keep flowing when it can increase entropy. When the incremental benefits for both parties can go up, can increase, there will keep on be the transfer of money, in the financial transaction. So for further discussions, this Dylan Bromberg's molecular driving forces describe this very nicely. So I urge you, if you are interested, please take a look at this book. So now, when the entropy can be increased no further by net changes in any degree of freedom, here we have been considering the exchange of energy, right? So as to maximize entropy, exchange of energy in terms of thermal energy, right? And therefore that is the heat interaction, isn't it? That is measured by the driving force, for that is measured by the inverse of temperature. When the entropy can no further be increased, then the system reaches its rest equilibrium state. There is no net driving force. That is why when we wrote the criteria for equilibrium, dou S by dou U is 0, it didn't mean temperature was 0. It is the net driving force for in the system between the two subsystems. So 1 by T for the subsystem A and 1 by T for the subsystem B. The difference was when it became 0, then there is no further driving force. Now you have reached a state of equilibrium or rest. This is determined therefore by the equality of the temperatures, analogous to the net benefits of the both parties being equal, right? So money for gadget transaction. Of course, please keep in mind that there is an idealization of business transactions in this analogy. Money does not always get exchanged to everyone's maximum benefit. That's an utopian idea, right? Sadly, but anyways, so keeping in mind that limitation, I hope you understand this analogy of what temperature is. So the equality of temperatures of the two systems A and B, subsystems A and B at equilibrium, is illustrated by this figure. So these two essentially represent the equilibrium states, the rest states finally, of the system A and system B. So this is the plot of entropy versus internal energy. All right. So this is some function. Of course, it has to be a monotonic function. When energy increases, entropy has to increase. So some arbitrary monotonic function has been plotted. So the state of equilibrium when A and B are in equilibrium with each other, it doesn't mean that UA is equal to UB. After all, that is not true. Nor does it mean that SA is equal to SB. That is also not true. What is true is that the slope dou S dou U for subsystem A is equal to the slope dou S dou U for the subsystem B. This is what you look for, and if you draw slopes at different points similarly for both curves and see where the slopes match, and that is where the systems reach equilibrium, because there is no additional driving force. Both sides are driving force the same, so there is no net driving force for the thermal energy to be exchanged from either system A to system B or system B to system A. Equality of temperature means the equality of slopes of the curves S versus U. Of course, this is all drawn at constant V and N. Note that SA is not equal to SB, UA is not equal to UB. Only the slopes are equal, which means the temperatures are equal. With this, we come to the end of this lecture on understanding what the intensive property temperature is. I hope this was clear to you. If there are any questions, as always, please feel free to contact me. Place your comments on the YouTube channel comment section, or you can reach me to my email, or you can contact me otherwise. All right, I look forward to receiving your feedback on this and all the other lectures as well. Thank you very much for listening to this lecture. You have a wonderful day. Thank you.